Hey class, how are you doing? It should be Wednesday today, and you should already have this wave spring activity handout. Normally this is a activity that you'd be doing hands-on, but I'll be doing it with you right now using some simulations that you've seen me use before. All right. So the first thing that I've given you is that you've got you don't have to worry about the general instructions at this point, or the required materials. Whoops. Let me go ahead and clear the ink from the page. Okay, we're just going to start right with the activities. So different types of waves. It says stick tabs of tape at regular intervals along your spring. Don't worry about that. It's just I'm going to show you what transverse versus longitudinal waves look like using a simulation. All right, first thing I want to show you is and I kind of showed a little video of this yesterday, but first thing I want to show you is just a transverse wave. Sorry there, I had to change a few settings here. I was playing around with it a little bit of my own. All right, so I'm going to show you if we pulse. So one disturbance to the medium transfers all the way through the medium, and then it rebounds off the fixed end and comes on back. All right, pause that, restart it. What we can do is show I can do this manually. Okay, so I can just grab the wrench and give it a little flick. Okay. If I change the dampening, what you see is that it's going to just die down. It's like a source of friction within the wave. Okay, so even if I send it a big pulse, it dies down very quickly. But without any dampening, the wave would just keep going back and forth all the way, as long as I run the simulation, I guess. Okay. Now, if I change the tension, higher tension means it goes faster. All right, and lower tension, you can see it slows right down, which is pretty unrealistic, but we're going to leave it somewhere up here. All right, let me restart that. And the third option for the simulation is, wow, oscillation. Let's turn the frequency down. This is going to get out of control very quickly. Okay, we're going to talk about more of this one in a second here. Pause. Okay, so that's that's your transverse wave. Now I've got a different simulation I'm going to fire up for longitudinal waves. This is just a speaker, and it's got some simulated air molecules. So you can visualize the sound moving through the actual air molecules. That's kind of neat. So if I change the higher amplitude, is going to create more compression. And a higher frequency is going to obviously create, well, madness to begin with here, but it should organize itself into more precise crests and troughs, but it doesn't look like it's doing that. So let me let me just restart that. Reset. Oh, I want the particles. All right, I guess I can't turn up the frequency. It just creates a mess on the screen. But you can see the compressions and the rarefactions as they're spreading out throughout the medium. All right, so that's your examples. That's activity 1. I'm going to pause this, and we're going to go back to the note. Activity 2. Reflection of transverse waves through fixed and free end medium. Okay. Again, ignore the actual instructions. Let me go back to the simulation. Give me a second here. Okay, so I'm going to go back to pulsing it. I want very little dampening, fairly high tension. So the wrench here represents the fixed end. And let me give this a pulse. And we'll see what happens with the reflected wave. You're going to see that it bounces and it inverts when it comes back. And you're going to see when it hits the first end, it inverts again and keeps going. Okay, So now, if I change that to a loose end, all right, we're going to see that there's a difference. Damping down a little bit more. Pulse width a little higher. Amplitude a little higher. You're going to see that it reflects, but it doesn't invert. Okay, when the ring is allowed to move up, when it's a free end, the reflected pulse, well, at that end it's a fixed end, but when it hits the ring end, the reflected pulse, it doesn't invert. It stays on the same side as the transmitted pulse. All right, so let's fill in the blanks together here for activity 2. Fixed end. Reflected pulse is inverted compared to the transmitted pulse or incident pulse. And for a free end, the reflected pulse is on the same side as the incident pulse. Can't forget good grammar. All right. At this point, okay, yeah, let's go on to do the third activity here. Okay, you can pause this if you need to finish copying. Otherwise, let's move on. Don't forget, let me do this with you instead of just reading it off the page. Okay, activity 3, constructive and destructive interference of waves. We're going to see what happens when I send 2 pulses that are on the same side and then 2 pulses that are on opposite sides. Okay, want relatively lower, a little bit lower tension for this one. First thing that's going to happen, I'm going to send 2 pulses that are on the same side. Down a little bit. All right, there's my second pulse. Now what happens when they meet? All right, let me actually make that a little bit wider. Turn the tension back up a little bit. Sorry, I thought that was going to look a little bit better, but it didn't. Okay, I'm going to turn the damping completely off. And let's pulse it again. Okay, so what happens when they meet? You get for a split second, let me try and pause it this time. Whoops, restart. You can do it one more time. I'm going to pause it when they overlap here, if I can catch it. Okay, you can see right there we have a much larger pulse than either of the 2 that were sent. All right, so that's an example of constructive interference. Now the next one I'm going to show you, I'm just going to reset it and change this to a fixed end so that we get constructive interference, so that we get a crest when it meets a trough. We're going to see what happens here. All right, so there's my 2 pulses. Boom. Ooh, I almost got that. Okay, they actually cancel each other out. And you can see as they move away from each other, they reform and continue on their merry path. Okay, let's see if we can do this again here. Okay, let's step this. Step, and you can see that they completely cancel each other out, for 1 split second as they pass over each other. Okay, so that's an example of destructive interference. All right, let's go fill in the blanks. Okay, sketch the resultant collisions of the waves. Okay, so let's say we have a pulse and a pulse, or a crest and a crest, sorry. All right, two crests traveling towards each other. When they meet, we get a supercrest. It could also be called constructive interference. Okay, and then I'll do a little bit smaller one for the destructive interference. So for this one, we've got a crest meeting a trough. And when they meet, they cancel each other out. The medium just looks flat for a split second. Okay, but we can show that we have, the energy is still there. It just temporarily canceled one. The crest canceled out the trough. Okay, so this is called destructive interference. Okay, how am I doing for time? I got 12 minutes going on here. Okay, I got 3 more minutes. Again, take a second, copy that down. Okay, so now we're going to do an example of what standing waves look like. So I'm going to go back to my simulation. And this time I'm going to set up oscillations. And I want to put on a little bit of dampening because I don't want my standing waves going out of control here. Now you have to change the frequency. The trick here is to change the frequency to get the waves stand. You can see down at the end here, they are kind of matching up with each other. Okay, I have to turn the dampening off a little bit more. Almost getting there. Oh, they're almost syncing up now. I'm going to turn the frequency down and restart it. Okay, let's see what happens here. There we go. Okay, it's not quite a perfect standing wave, but it's close. So you can see that there's places on the simulation where that they're actually the particles aren't actually moving. Oh, no, that's not really good. It's not good to show it here. I need to get it exactly. Let me restart that with a different frequency here. I think this one might do it. Okay, you can see this particle here. This guy, I wish I could write on this board. I wish you could see what I'm pointing at right now. Oh, there it is. Okay, so this particle here, keep track of that one, okay? You can see that it doesn't move very much at all from rest. Okay, it stays very close to the medium. And what you're going to see here is that's an area of complete destructive interference. Okay, that's called a node. All right, so if I keep playing that, that little particle there doesn't move much from its original location. Okay, that's called a node when we talk about standing waves. All right, let's go back to the activity. Make a couple notes here. All right, so it's forget about the actually doing the activity. I just want to use this situation here, this space here, to draw a standing wave and what it looks like with labeling the nodes. Alright, so I'm going to make just a dotted line to show the middle of the Alright. Now, the hard part's going to be to actually draw this nice sine wave. I'm going to give it a shot. Okay, I'm going to resize this to match. Okay, so we've got one set of waves. Now, the reflected set, if this is a fixed end, is going to be the inverse of the transmitted wave. Alright, and that's kind of the pattern that is set up when we talk about standing waves. Now, these places in here are what we call nodes. Some textbooks have them at the end. I believe your textbook does not. If their number of nodes are off by 2, it's because they've included the endpoints as nodes. Other than that, let's just assume that the endpoints are not nodes for now. Okay, so we'll call those nodes. And then the actual, the crests and the troughs, where the constructive interference happens, those are called antinodes. Alright, so nodes are where, when we have a standing wave, nodes are where there's destructive interference, and antinodes are where there's constructive interference. Alright, I'm going to sign off now. I'm going to put your homework on the board for today.